Welcome to the 33rd lecture of the MOOC on parallel algorithms. We will continue with our discussion of interconnection networks that are related to hypercubes. In particular, when the previous lecture stopped, we were talking about shuffle exchange graphs. So, let us continue with that discussion. A shuffle exchange graph has two kinds of edges. There are shuffle edges and exchange edges. We saw a three-dimensional shuffle exchange graph in the previous class. Today, let us see first a shuffle exchange graph of dimension 1. A shuffle exchange graph of dimension 1 has two nodes named 0 and 1. There is an exchange edge between them because these two nodes differ in the least significant bit. And when 0 is cycled to the left, we get 0 again. Therefore, we have a self loop involving the vertex 0, and when 1 is left shifted, we get 1 again. So, we have a self loop involving vertex 1 as well. So, this is a shuffle exchange graph of dimension 1. A shuffle exchange graph of dimension 2 involves vertices 0 0, 0 1, 1 0 and 1 1. There is a self loop involving 0 0 and 1 1, because when these strings are left shifted, we keep getting the same string. There is an exchange edge between 1 0 and 1 1, and there is an exchange edge between 0 0 and 0 1. When 0 1 is left shifted, we get 1 0, and when 1 0 is left shifted, we get 0 1. So, there are two edges between 0 1 and 1 0. So, this is a shuffle exchange graph of dimension 2. And then coming to dimension 3, which we saw in the last class, the nodes are numbered with 3-bit binary strings. 0 0 left shifted will give us 0 0 0. 1 1 left shifted will give us 1 1. So, there are self loops to them. Then there is an exchange edge from 0 0 to 0 0 1, because they differ in the least significant bit. And then a left cyclic shift of 0 0 1 will give us 0 1 0, and a right cyclic shift will give us 1 0 0. 0 1 0 and 0 1 1 are adjacent through an exchange edge. 1 0 0 and 1 0 1 are adjacent through an exchange edge again. 1 1 0 and 1 1 1 are again adjacent through an exchange edge. When 0 1 1 is cyclically left shifted, we will get 1 1 0. When that is cyclically left shifted, we will get 1 0 1. So, this is a shuffle exchange graph of dimension 3. So, you can construct shuffle exchange graphs of higher dimensions in this manner. In particular, for dimension r, take the 2 power r binary strings of length r, and then draw the exchange edges between nodes that differ in the least significant bit. Shuffle edges are between vertices that are cyclic shifts of each other. So, as we saw in the last class, the diameter of such a graph is order of r. That is, in particular, you can go from vertex u1 through ur to vertex v1 through vr by fixing the bits one at a time, and this will take at most 2r steps for any u and any v. Therefore, the diameter of a shuffle exchange graph of dimension r is order of r. What about bisection width? It can be shown that the bisection width is order of n by log n, and the proof is quite interesting. Let us embed the shuffle exchange graph on the complex plane. Let us define omega r as e power 2 pi I by r, which is the rth root of unity. Now, consider node u equals u1 through ur of SEGR. Let sigma of u be the complex number to which u is mapped. So, we map the network onto the complex plane using a function sigma of u. Now, sigma of u is defined in this manner. This is how we define sigma of u. Sigma of u is defined using the rth root of unity. Now with this definition we find that sigma of u1 through ur minus 1 1 is, that would be 1 at the last position. That is because u r equal to 1 here. If the last bit happens to be 1, then this is what sigma of u is going to be. But this can be written as plus 1. But the quantity within the brackets happen to be sigma of u1 through ur minus 1 0 plus 1. So what we find is that the complex number to which u1 through ur minus 1 1 maps to is 1 more than the complex number to which u1 through ur minus 1 0 maps. So if in the complex plane we consider these two vertices, if I call this one u and this u prime, we find that u and u prime are mapped 1 unit apart. The difference between u prime and u is real number 1. Sorry, it's the other way around. U prime will be to the left and u will be to the right, because u has 1 at the last bit. Now this is nothing but an exchange edge. So what this establishes is that exchange edges under this mapping are parallel to the real line and have a length of unity. The length of all exchange edges is unity under this mapping. So now we are effecting a mapping of the shuffle exchange graph of dimensions r onto the complex plane, and we find that every exchange edge are mapped 1 unit apart. Now let us see how the shuffle edges are mapped. To find out how shuffle edges are mapped, let us consider this quantity. Sigma of u is the complex number to which u is mapped. We multiply that complex number with omega r, substituting for sigma. This is what we get. Now taking omega r inside, we find that we have plus u1. That is because omega r power r equal to 1. Omega r happens to be the rth root of unity. Therefore, omega r power r equal to 1. Therefore, this is what we get. Now this is nothing but sigma of u2 through ur u1. But u2 through ur u1 is a shuffle neighbor of u1 through ur. And on the complex plane, these two quantities are related by a multiplication with omega r. But multiplication with omega r corresponds to anticlockwise rotation by 2 pi by r radians, which means this is equivalent to cyclic left shift. Correspondingly, cyclic right shift will correspond to clockwise rotation by 2 pi by r radians. So now this allows us to sketch shuffle exchange graphs on the complex plane. In particular, let us consider the 3-dimensional shuffle exchange graph. This is the imaginary axis and this is the real axis. At the origin we have 0 0 0 and 1 1 1. That is because the cube roots of unity when all added together will give us 0. The exchange neighbor of 0 0 will be 0 0 1. When 0 0 1 is rotated anticlockwise by 2 pi by 3 radians, we will get the node corresponding to 0 1 0. When that is rotated by another 2 pi by 3 radians, we will get 1 0 0. And when that is rotated again by 2 pi by 3 radians, we will come back to 0 0 1. The exchange neighbor of 1 1 will be similarly 1 1 0. So there is an exchange edge from 1 1 0 to 1 1 1, just as there is an exchange edge from 0 0 to 0 0 to 0 0 1. The exchange neighbor of 0 1 0 will be 0 1 1. From 0 1 1, we come to 1 1 0 by a 120 degree rotation. From 110 we can go to 101 also by a 120 degree rotation, which also happens to be an exchange neighbor of 100, and then there is a shuffle edge between 011 and 101. The three-dimensional shuffle exchange graph has 4 exchange edges, all of them are marked now, and the shuffle edges are also marked. So, this is the plotting of a three-dimensional shuffle exchange graph on the complex plane. Similarly, if you plot the 4-dimensional shuffle exchange graph on the complex plane, we find that several nodes map to the origin. As you can verify, 00001111, 1010 and 0101 all map to the origin. Both 0001 and 1011 map to 0.10. Similarly, 0010 and 0111 map to 01, and diametrically opposite we have 1000 and 1101 mapping to 0 minus 1, and minus 10 has 0100 and 1110. So, we have exchange edges of this sort. There are shuffle edges between these nodes. A shuffle in this case corresponds to a pi by 2 radians rotation, which is a 90 degree rotation on the complex plane. Now, 0010 has an exchange edge to 0011. Rotating from 0011, so this is a shuffle edge. So, these are the shuffle edges involving 1100 and its cyclic rotations. There are exchange edges like this, 01102, 0111. Similarly, here also we have an exchange edge, 1100 to 1101, and there is an exchange edge from 1000 to 1001. So, those are the exchange edges and the shuffle edges of a 4-dimensional shuffle exchange graph. So, in the case of a 4-dimensional shuffle exchange graph, we find that there are several vertices mapping to the same complex number. That is because in this case we have what are called degenerate necklaces. But first let me define what is called a necklace. On the complex plane we find that necklaces form. A necklace is a cycle formed by shuffle edges. If you look at the plotting of a 3-dimensional shuffle exchange graph, we find that we have 2 necklaces of length 3 each. So, in particular, in shuffle exchange graph R, embedded on the complex plane can have necklaces of R points. Of course, no necklace can have more than R points because every shuffle edge corresponds to a 2 pi by R radians rotation. But we can have necklaces of R points. These are full necklaces. Some necklaces may not be full. These are called degenerate necklaces. For example, in SEG 4, consider sigma of 1010. When 1010 is cyclically left shifted, we get 0101. When that is cyclically left shifted, we get 1010 again. What that means is that omega 4 squared multiplied by sigma of 1010 is equal to sigma of 1010. because every shuffle edge corresponds to a rotation by 2 pi by 4 radians. Since omega 4 squared is not equal to 1, this implies that sigma of 1010 equal to 0. Similarly, sigma of 0101 also is 0. As we saw in the figure, 0000, 1111, 1010 and 0101 all map to the origin. These form the degenerate necklaces. So, degenerate necklaces happen when we have cycles within the binary representation. For example, the binary representation of 1010 is cyclic. It has the same unit 1010 repeating multiple times. So, when the binary representation is cyclic, then we have degenerate necklaces. But then when you consider a full necklace, if any node in the shuffle exchange graph maps to a complex number which is not the origin, then by rotating by 2 pi by r radians from there, you will complete a full cycle and come back to the starting node. Therefore, any node which is mapped to a non-origin will correspond to a full cycle. Now, why did we do all this? We want to find the bisection width of a shuffle exchange graph. First, what I want to claim is that at most order of n by log n nodes are at the origin. This is because if sigma of u equal to 0, that is u is mapped to the origin, then u prime, the exchange neighbor of u, is not at the origin. It will have to be at either 1 0 or minus 1 0, because an exchange edge is of length 1 and is parallel to the real axis. Therefore, u prime will be mapping either to 1 0 or minus 1 0. In that case, there is a full necklace containing u prime. So, what we find is that for every node that maps to the origin, its exchange neighbor is in a full necklace. There are at most n by log n full necklaces. There can be at most n by log n full necklaces because a full necklace by definition has log n nodes. So, there could be at most n by log n distinct full necklaces. When you consider a full necklace, at most 2 nodes of the full necklace can be on the real line. Therefore, the number of nodes at the origin is order of n by log n. Once again, if a node falls at the origin, its exchange neighbor falls in a full necklace, then that itself accounts for n by log n vertices. There can be at most n by log n full necklaces, therefore, at most order of n by log n vertices will fall at the origin. By the same argument, we can show that order of n by log n vertices fall on the real line. If a node falls on the real line but is not at the origin, then it will be a part of a full necklace, and in any full necklace at most 2 nodes can fall on the real line, and there are at most n by log n full necklaces. So, at most n by log n vertices can fall on the real line. Similarly, at most n by log n edges cross the real line. Why is this so? When you consider a full necklace, at most 2 edges in the full necklace can cross the real line. The remaining nodes are either above the real line or below the real line. Therefore, every other edge is strictly above the real line or strictly below the real line. So, at most 2 edges of any full necklace can cross the real line. And then, if an edge is on the real line, it is an exchange edge and its endpoints are on the real line. And we have already bound the number of nodes on the real line to be order of n by log n. Therefore, putting all this together, we can say that at most n by log n edges cross the real line or are on the real line. Now, let us remove all edges that are on the real line or cross the real line, or let us say we remove all edges that touch the real line or cross the real line, that is has one of the endpoints on the real line or cross the real line. The graph splits. Let us consider the vertices above the real line and the vertices below the real line. So this is a partition of the graph. But is it a bisection? It will be a bisection if the number of vertices above the real line is equal to the number of vertices below the real line. In fact, that indeed is the case. Therefore, this is indeed a bisection, and the number of edges that we have removed is order of n by log n. Therefore, we are in fact getting a bisection. But how do we show that the number of vertices above the real line is equal to the number of vertices below the real line? Let us consider sigma of the bitwise complement of u. This is going by the definition. Similarly, sigma of u1 through ur is ur, and when we add them together we find that this is, but then what is this? This is the sum of the rth roots of unity, which we know is 0. What it means is that the bitwise complement of a vertex u gets mapped to the additive inverse of sigma of u. In other words, if sigma of u happens to be below the real line, then sigma of u bar happens to be above the real line, and vice versa. Therefore, the number of nodes that are below the real line is equal to the number of nodes that are above the real line. So, putting this together with our earlier argument, we find that the bisection width of a shuffle exchange graph of dimension r is 2 power r by r, order of 2 power r by r. Or in other words, if r equal to log n, we have a bisection width of order of n by log n. So, shuffle exchange graphs like hypercubes have this nice property. They have a small diameter and a large bisection width. Now, let us see a network which is closely related to shuffle exchange networks and also have some nice properties. After that, we will see some simulation results in both of them. These are De Bruijn graphs. An r-dimensional De Bruijn graph defined on 2 power r vertices. These vertices are numbered using r bit strings. The edges of this network are defined like this: from u1 through ur minus 1 ur, we have an edge to u2 through ur 0, and we have an edge to u2 through ur 1. That is, to obtain an out neighbor of a vertex, we have to cyclically left shift the binary representation of the vertex. In that case, u1 will come at the least significant position, we will have u2 through ur at the most significant positions, and then we get one neighbor, and then by exchanging the last bit, we will get the other neighbor. So, as we can see, the correspondence between shuffle exchange graphs is immediately evident. When you cyclically left shift, you get one neighbor which is the same as the shuffle neighbor, and then by flipping the last bit, we will get another neighbor which happens to be the exchange neighbor of the shuffle neighbor. In other words, a De Bruijn graph is obtained by contracting the exchange edges of a shuffle exchange graph of the same dimension. We will come to that later. So, once the edges are defined in this graph, we also define some edge labels. The edge which is directed to u2 through ur0 will be labeled 0, and the edge which is labeled to u2 through ur1 will be labeled 1. So, if you label the edges in this fashion, we find that u1 through ur minus 1 ur by an extension of the definition, we find that there are two incoming edges to it. This will be labeled UR each. So you can see that in this case, the out degree of every vertex is equal to the in degree of every vertex, which is equal to 2. So this is a 2 regular graph, or the underlying undirected graph is a 4 regular graph. Every vertex has a vertex degree of 4. So you could say the underlying undirected graph is 4 regular. That's because every vertex has 4 neighbors, 2 in neighbors and 2 out neighbors. There are some interesting recursive properties to the Bruijn graph. We find that an r-dimensional de Bruijn graph, as I mentioned just now, is obtained by from an r plus 1 dimensional shuffle exchange graph by contracting the exchange edges. Pictorially, let us take the 3-dimensional shuffle exchange graph. And then contract the exchange edges. In particular, we are contracting 000 and 001 into one single vertex. These two vertices agree on the two most significant bits. Therefore, the result of the contraction will be numbered using those two bits. So 000 and 001 contracted together will form 00. These two vertices contracted together, and these two vertices are also contracted together. These are contracted together, and these are contracted together. 00 has an edge to itself. 010 and 011 contract to give us the vertex 01, and 100 and 101 contract to give us the vertex 10. 110 and 11 contract to give us the vertex 11. The remaining edges can be fitted like this. You can verify that we have these remaining edges, and the edge labels would be like this. So the picture below is a de Bruijn graph of dimension 2, and here we have a shuffle exchange graph of dimension 3. So the relationship between the two networks is readily apparent. The shuffle exchange graph becomes a de Bruijn graph if you contract every single exchange edge of the shuffle exchange graph. The main difference is that in de Bruijn graph the edges are directed and every edge has got a label too. And another nice recursive property that we observe is that a de Bruijn graph of dimension r plus 1 is the line graph of DBGR, the r-dimensional de Bruijn graph. You would recall from your graph theory that the line graph of G is obtained by taking a vertex for each edge of G and making two of the new vertices, that is the vertices in the line graph, adjacent if and only if the corresponding vertices are adjacent in, the corresponding edges are adjacent in G. Every vertex in the line graph corresponds to an edge in the original graph, and two vertices in the line graph are adjacent if and only if the corresponding edges in G are adjacent. So I will leave the proof as an exercise for you. So we will see some simulation results on these two networks in the next class. That is it from this lecture. Hope to see you in the next. Thank you.